All right, welcome back. We're diving straight into Chapter 4 of our AI Fundamentals series, and this one's a biggie, machine learning. I mean, this is the engine that powers pretty much all of modern AI. So if you've ever found yourself wondering how a machine actually learns, well, you're in exactly the right place. Let's get into it.
So, to kick things off, let's think about a really classic problem, one that researchers have been banging their heads against for decades. How on earth does a machine learn to read human handwriting? I mean, look at this. It's just a simple digit, right? But our handwriting is messy, it's inconsistent, it's full of little quirks. How can a computer possibly make sense of all that chaos?
Well, to solve this puzzle, the AI community came up with something called the MNIST dataset. You're going to hear this name a lot. It's basically a massive collection of thousands and thousands of scanned, handwritten digits that have already been labeled. And what makes this such an amazing challenge is that some of them are genuinely hard to read, even for us. You know, you'll see a 7 that looks an awful lot like a 4. It's that real-world messiness that makes this problem so interesting and so tough to solve.
Okay, so here's our game plan for today. We're going to start with this digit recognition problem, then we'll look at the old-school way people tried to solve it. After that, we'll break down the main types of machine learning, spending a little extra time on what's called supervised learning. And then we'll wrap up with a really important warning that everyone in this field needs to know about.
So, let's nail this down. Our mission, should we choose to accept it, is to build an AI that can look at an image of a messy, handwritten digit and correctly tell us what number it is, from 0 all the way to 9.
But before we get into the cool, modern stuff, let's take a step back. How did people try to do this before machine learning came along? The main approach was something called an expert system. The whole idea was to sit down and manually program a bunch of explicit rules for the computer to follow. Let's see how that would play out with our digit problem.
You'd probably start with something pretty logical, right? Like this. A 0 is basically just a single loop. So you'd tell the computer, hey, if the black pixels form a single closed loop, then the label is 0. Simple enough.
And you just keep going like that. Okay, what's an 8? Well, it's pretty much 2 loops kind of stacked on top of each other, so boom, we add another rule to our system for that. So far, this seems manageable, right?
And for the number 1, you might write a rule like, if the black pixels form a straight vertical line, call it a 1. I think you can probably see where this is headed. You'd have to sit there and painstakingly create these super specific, detailed rules for every single digit.
And right here is where the whole thing just completely falls apart. I mean, think about it. What about a 1 that's written with a little tilt, or a 0 that has a tiny gap in it? This whole expert system approach is incredibly brittle. The rules are way too rigid. For every single rule you write, you need like a dozen exceptions. It's a nightmare. It's slow, it's impractical, and honestly, it's pretty much impossible to scale. There had to be a better way.
And that better way, of course, is machine learning. And this wasn't just a small improvement, it was a fundamental shift in thinking. Instead of us humans trying to explicitly tell the computer all the rules, we just show the computer a bunch of examples and let it figure out the rules for itself. This idea is the absolute game changer.
So machine learning is usually broken down into 3 main categories. First up, you've got supervised learning. The goal here is to predict a correct label. Think identifying a traffic sign. Then there's unsupervised learning, where we want to discover hidden patterns or structures in data, like a company figuring out different groups of customers. And finally, you have reinforcement learning, where an AI agent learns to operate in some environment, like a self-driving car learning the rules of the road.
We're going to zoom in on supervised learning first, mostly because it's the most common type you'll run into. And the name itself gives you a perfect clue for how it works. It's like there's a teacher or a supervisor guiding the machine while it learns.
So here's the absolute key takeaway. In supervised learning, you feed the algorithm a massive data set of examples that already have the correct answer attached. For our digit problem, that means showing it thousands of images of the number 7 that are all clearly labeled 7. The algorithm's job is then to churn through all that data and find the hidden patterns that consistently connect those images to their labels.
Now, supervised learning problems typically come in 2 main flavors. First, there's classification. That's exactly what our digit recognizer is trying to do. It's predicting a specific category, or a class. Is this a 0, a 1, a 2, and so on. The other type is regression. Here you're not predicting a category, you're predicting a continuous number. Something like, what's the price of this house going to be? Or how many clicks will this ad get tomorrow?
All right, so let's do a quick flyby of the other 2 types, which are fascinating because they work without a teacher giving them all the answers up front. With unsupervised learning, you basically hand the machine a ton of data with no labels at all, and you just say,
find something interesting in here. A great example is a grocery store discovering customer groups they never even knew existed just by looking at purchase data. Then you have reinforcement learning. Here, there are no preset labels, but there is feedback. Think of it like training a dog with treats. An AI agent tries out different actions, gets a reward for a good one and a punishment for a bad one, and through tons of trial and error, it eventually learns the best strategy.
Okay, before we wrap up this session, there is one absolutely crucial concept that you have to understand no matter what kind of machine learning you're doing. It's a dangerous trap called overfitting.
So what is overfitting? It's what happens when your model gets, well, too smart for its own good on the data you trained it on. It doesn't just learn the real underlying patterns, it also starts to memorize all the random noise and the weird specific quirks in your training data. The result? You get a model that looks like a genius on paper, but the moment it sees brand new, real-world data, it just completely falls flat.
This quote is a fantastic and kind of funny way to think about it. Imagine you're trying to build a model to predict hit songs. You find a pretty good rule, like if the song is about love and has a catchy chorus, it'll be a hit. But then you see some exceptions, so you improve your rule. You add except if the song mentions Sweden or yoga. See what's happening? By adding these bizarre, hyperspecific exceptions, you've created a model that perfectly explains the past but is totally useless for predicting the future. That, in a nutshell, is overfitting.
So how do we dodge this bullet? Thankfully, the solution is actually pretty simple and elegant. You never, ever use all of your data for training. You split it. Use one chunk, the training data, to teach your model. Then, to get a real, honest measure of how well it works, you evaluate it on the second chunk, the test data, which the model has never, ever seen before.
And this brings us to the ultimate goal of pretty much all machine learning. It's not about memorizing the past or getting a perfect score on the data you've already seen. The true goal is generalization. The ability to take the patterns you learned from the training data and apply them accurately to new, unseen situations in the future.
So, there you have it. We've gone from these clunky, hard-coded rules to machines that can actually learn from examples. We've looked at the 3 main ways they learn, and we've talked about the critical danger of overfitting. That is a massive first step. So the real question is, now that you get the basic concepts, are you ready to see your first machine learning algorithm in action? Because that's exactly what we're going to do in our next session. We'll see you there.